Video by learning the second derivative test. So why should we use second derivative test? Because from our second derivative test, we can check the signs of the concavity. Okay, so concavity is, for example, a smiley graph here. This graph is concave up, and you will find that you will have relative minimum. And for this shape here, you will have concave down. So from concave down, therefore, you can say that you have relative maximum. Okay, so how to test this? The way to test this is you need to find f double prime, and then you need to check of three conditions here. So from your f double prime, when you put in the value of x, the value of your critical number, if it gives you a positive number, therefore you can say that you have a smiley graph. Okay, if it is positive, you smile. You have a smiley graph, therefore you can conclude that f has a relative minimum at the specific critical point. For part B, if your f double prime of your value of x, the critical point, give you a negative value, you will have concave down. So when you have concave down, therefore it is clear that you have relative maximum. So if your f double prime is less than 0, you can say that f has relative maximum at that specific point x naught. Okay, and finally, if your f double prime give you the value of 0 exactly, you can say that the test fails. Okay, the test is inconclusive. You cannot conclude you have relative maximum or you have relative minimum or you have neither. Okay, so what you should do is you need to return back and do the first derivative test. Let's apply that in this example here. Use the second derivative test to find x coordinate of the relative extrema for the function x to the power of 4 minus 2x squared. So you have 4 steps that you need to follow. The first one, find f prime x. The second one, find your critical point. The third one, test for your second derivative test. And finally, let's conclude your answer. So first of all, let's find our f prime x first. So this is just power rule, so bring down the power reduced by 1. So this is 4x cubed minus 4x. So settle with that. Secondly, let's find our critical point. The first one, let's find f prime x equal to 0. So let's take this value here equate to 0. Let's factorize, and then we'll get to the value x equal to 0, x equal to negative 1, and x equal to 1. So keep this first. Next, let's find f prime x is undefined, so you don't have any denominator, therefore you have none. Next, let's find our domain for f so that we are sure that our x chosen is really a critical point. So let's see here, this is just polynomial, therefore your x is all real number. Therefore, you can accept all the points here as your critical points. Therefore, critical points are x equal to 0, x equal to negative 1, and x equal to 1. Now, let's go to step number 3, which is we want to check our second derivative test. So, from f prime x, let's further differentiate this. So, this is just power rule, bring down the power reduced by 1. Therefore, this is your f double prime, 12x squared minus 4. So, now we have finished finding the second derivative. So, now let's test one by one of our critical point. First of all, we have x equal to 0. So f double prime 0, this is just equal to 12 times 0 squared minus 4. So this is negative 4. So negative 4 is less than 0. So you have this concave down here. So this shape here shows that this is relative maximum. So let's conclude. Therefore, we have relative maximum at x equal to 0. Now let's proceed with the point x equal to negative 1. So let's fill in f double prime negative 1. So whenever you see x, let's substitute with negative 1. So the results will give you 8. 8 is positive, so it is a smiley graph, concave up. Therefore, it's very clear to us that you have relative minimum. So let's conclude. You have relative minimum at x equal to negative 1. And finally, let's test our last point, x equal to 1. So f double prime 1, let's substitute here. F double prime 1 is 12, 1 squared minus 4. So this will again give you the value of 8. So this is positive. Smiley graph, concave up. So it's very clear to us that you have relative minimum. Therefore, let's conclude you have relative minimum at x equal to 1. So that is how you should do a second derivative test. So that's all for this chapter. We will see the application of this chapter in the next chapter, which is optimization. Assalamualaikum warahmatullahi wabarakatuh.